You sit in a quiet room, perhaps late at night, and you decide to examine something closely. Maybe it's the surface of your desk, the texture of fabric, or the palm of your hand. At first glance, everything appears solid, continuous, predictable. The closer you look, the more detail emerges. Fibers become visible in the fabric. Lines and ridges appear on your palm. This is how we expect the world to behave. The closer we examine something, the more we should understand it. The finer the detail, the clearer the picture should become. But somewhere in the depths of reality, this reasonable expectation breaks down completely. The universe, it turns out, does not reward closer inspection with greater clarity. Instead, the most fundamental layers of existence seem to operate by rules so strange, so divorced from everyday experience, that each new discovery raises more questions than it answers. We find ourselves in the peculiar position of knowing more about reality than ever before, while simultaneously confronting the possibility that reality itself may be far more mysterious than we had imagined. Consider what happens when physicists try to look closely at light. For centuries, light seemed straightforward enough. It travels in straight lines, bounces off mirrors, bends through lenses. But when researchers began examining individual particles of light, something unsettling emerged. They designed an experiment so simple that it can be performed on a laboratory bench. Yet its implications are so profound that physicists still argue about what it means more than a century later. The experiment involves nothing more than a barrier with two parallel slits and a screen to catch whatever passes through. When ordinary objects like marbles are thrown at such a barrier, they pass through one slit or the other and create two bands on the screen behind. This matches our expectations perfectly. When waves are sent toward the same barrier, something different happens. The waves pass through both slits simultaneously, interfere with each other, and create multiple bands on the screen. This also makes sense. Waves behave like waves. But when individual particles of light are sent toward the barrier, one at a time, something extraordinary occurs. Each particle arrives at the screen as a single point, like a marble. Yet after thousands of individual particles have been sent through, the pattern they create is not two bands, but multiple bands, exactly like the wave pattern. Somehow each individual particle seems to have passed through both slits simultaneously and interfered with itself. This is where intuition begins to falter. How can a single particle be in two places at once? The natural response is to try to catch the particle in the act. Researchers place detectors at the slits to determine which path each particle actually takes. But the moment they do this, the multiple band pattern disappears. The particles begin behaving like ordinary objects again, creating just two bands on the screen. The very act of trying to observe which slit the particle passes through seems to change the fundamental nature of what is happening. This is not a problem with the equipment or the method. The same results have been obtained with increasingly sophisticated technology over decades. The pattern emerges consistently. When no one is looking, particles behave like waves. When someone tries to look, they behave like particles. The universe appears to respond to the act of observation itself. If this were merely a curiosity confined to exotic particles in specialized laboratories, it might be easier to dismiss. But the implications extend far beyond light. The same wave-like behavior has been demonstrated with electrons, atoms, and even molecules containing thousands of atoms. In 2019, researchers successfully performed the experiment with molecules so large they contain 2,000 atoms each. These are not quantum specks invisible to the naked eye. These are substantial structures that nonetheless exhibit the same mysterious behavior. What emerges is a picture of reality that seems to shift depending on how closely we examine it. At the scale of everyday experience, objects have definite properties. A ball is either here or there, moving or stationary. But when we drill down to the fundamental level, definiteness seems to evaporate. Particles exist in what physicists call superposition, a condition where they possess multiple contradictory properties simultaneously until the moment someone tries to measure them. Werner Heisenberg discovered another limitation that appears to be built into the fabric of reality itself. His uncertainty principle reveals that there are pairs of properties that cannot be known precisely at the same time. The more accurately you determine a particle's position, the less you can know about its momentum, and vice versa. This is not a limitation of measurement tools or techniques. It appears to be a fundamental feature of how reality operates at its deepest level. The implications are unsettling. Classical physics suggested that with perfect instruments and enough time, every property of every particle could be measured with arbitrary precision. Reality seemed like a vast clockwork mechanism whose every gear and spring could eventually be mapped. Heisenberg's discovery suggests instead that there are questions about the physical world that have no definite answers, not because we lack the ability to find them, but because definite answers do not exist. Recent experiments have pushed these boundaries even further. In 2024, researchers demonstrated what they call negative time, showing that under certain quantum conditions, quantum models describe this process using what researchers refer to as negative time, a technical result within the formalism rather than a literal reversal of time. The photons emerge from a cloud of atoms before they have finished passing through it, according to quantum clocks designed to measure the process. This does not violate causality or allow time travel, but it does reveal that even time itself behaves strangely at the quantum level. Another phenomenon challenges our basic understanding of space and locality. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein famously dismissed this as spooky action at a distance, convinced it revealed flaws in quantum theory. But decades of increasingly precise experiments have confirmed that entanglement is real. Particles separated by miles or potentially light years remain connected in ways that seem to transcend the speed of light limit that governs all other interactions. In 2015, researchers at Delft University performed what they called a loophole-free test of this phenomenon, closing the last remaining experimental doubts about its reality. The results were unambiguous. Entangled particles do influence each other instantaneously across arbitrary distances. The universe appears to contain connections that operate outside the normal rules of space and time. Perhaps even stranger is the phenomenon of quantum tunneling, where particles pass through barriers they should not have enough energy to overcome. Classical physics says this is impossible. A ball thrown at a wall will bounce back unless it has enough energy to break through or climb over. But quantum particles regularly tunnel through energy barriers as if the barriers were not there. This is not merely a theoretical prediction. Quantum tunneling is essential to how the sun generates energy and how many electronic devices function. In 2025, the Nobel Prize in Physics was awarded for demonstrating that quantum tunneling can occur in macroscopic systems containing billions of particles. What was once confined to individual atoms and electrons now appears in objects large enough to be visible. The boundary between the quantum world and the everyday world is not as clear as it once seemed. Each of these discoveries reveals the same unsettling pattern. The deeper we probe into reality, the less it resembles the stable, predictable world of our everyday experience. Properties that seem fixed and definite at one scale become fluid and probabilistic at another. Space and time, which appear absolute and universal in ordinary life, prove to be more flexible and contextual than we had imagined. Yet these are not speculative ideas or philosophical thought experiments. They emerge from the most rigorous experimental work in the history of science. Quantum mechanics, despite its strangeness, has been tested more thoroughly than any theory in physics. Its predictions have been confirmed to extraordinary precision across countless experiments. The technology that surrounds us, from computer chips to medical imaging devices, relies on quantum effects working exactly as the theory predicts. This creates a peculiar situation. We have a theory that works perfectly for predicting and controlling quantum phenomena, yet no one fully understands what it means. Physicists can calculate the probability that a particle will be found in a particular location, but they cannot say where it actually is before the measurement. They can predict the statistical outcomes of quantum experiments with stunning accuracy, but they cannot explain why individual events happen when and where they do. The more successful quantum mechanics becomes as a practical tool, the more mysterious it becomes as a description of reality. We find ourselves in the strange position of being able to manipulate the fundamental level of nature while remaining uncertain about what that level actually contains. It is as if we had learned to conduct a symphony perfectly while remaining unsure whether the orchestra exists when no one is listening. This creates a peculiar situation. We have a theory that works perfectly for predicting and controlling quantum phenomena, yet no one fully understands what it means. Physicists can calculate the probability that a particle will be found in a particular location, but they cannot say where it actually is before the measurement. They can predict the statistical outcomes of quantum experiments with stunning accuracy, but they cannot explain why individual events happen when and where they do. The more successful quantum mechanics becomes as a practical tool, the more mysterious it becomes as a description of reality. We find ourselves in the strange position of being able to manipulate the fundamental level of nature while remaining uncertain about what that level actually contains. It is as if we had learned to conduct a symphony perfectly while remaining unsure whether the orchestra exists when no one is listening. This tension between operational success and conceptual understanding becomes even more pronounced when we consider how quantum mechanics handles the concept of measurement itself. The theory divides the world into two distinct realms: quantum systems that exist in superposition and classical measuring devices that produce definite results. But this division creates an immediate problem. Where exactly does one realm end and the other begin? A particle detector is made of atoms, which are quantum mechanical objects. Those atoms interact with other atoms in circuits and displays, all of which are fundamentally quantum mechanical. At what point in this chain does the fuzzy quantum world give way to the definite classical world we experience? This question, known as the measurement problem, has no agreed upon answer. Some physicists argue that consciousness plays a role in collapsing quantum states. Others propose that the environment causes decoherence, washing out quantum effects. Still others suggest that all possible outcomes occur simultaneously in parallel universes. Each interpretation attempts to bridge the gap between mathematical formalism and physical reality, yet none has achieved consensus. The interpretations are not merely different ways of saying the same thing, they make different claims about the nature of reality itself. In one interpretation, particles have no definite properties until measured. In another, all possible realities exist simultaneously. In a third, there are hidden variables we simply cannot access. What makes this situation particularly striking is that the choice between interpretations has no effect on the practical application of quantum mechanics. Whether you believe in parallel universes or hidden variables, you will make identical predictions about experimental outcomes. The mathematical machinery of the theory remains the same regardless of what you think it means. This suggests something unsettling about the relationships between our theories and reality. We may have reached a point where our most successful scientific theories describe the behavior of nature without revealing its essence. The problem extends beyond quantum mechanics to other areas where closer examination yields greater mystery rather than clarity. Consider the nature of space and time themselves. Einstein's relativity revealed that these seemingly absolute features of reality are actually relative, depending on motion and gravity. Time passes differently for observers in different reference frames. Space contracts and expands depending on velocity. What had seemed like the fixed stage upon which physical events play out turned out to be part of the performance itself. But relativity, despite its conceptual strangeness, still preserves certain intuitions about causality and locality. Events have definite sequences, and influences propagate from place to place at finite speeds. Quantum mechanics challenges even these basic assumptions. The entanglement experiments reveal correlations that seem to transcend the speed of light, while quantum tunneling allows particles to appear on the far side of barriers without having travelled through the intervening space. Recent discoveries in quantum physics have pushed these puzzles to even more extreme lengths. Researchers have identified phenomena they call quantum scars, where chaotic quantum systems unexpectedly organize themselves into stable patterns that persist far longer than theory predicts. These scars represent a kind of quantum memory, where systems remember their initial conditions in ways that classical chaos theory says should be impossible. In another line of research, physicists have demonstrated something called quantum contextuality, which reveals that quantum systems do not possess definite properties independent of how they are measured. The same particle can yield different results depending on what other measurements are performed alongside the primary measurement. This goes beyond the observer effect to suggest that reality at the quantum level lacks the kind of objective, context-independent properties that our classical intuition demands. Perhaps most puzzling of all are recent experiments that seem to demonstrate backward causation in quantum systems. In these delayed choice experiments, researchers can decide how to measure a quantum system after the system has already interacted with the measurement apparatus. Remarkably, this future decision appears to retroactively determine how the system behaved in the past. The implications are difficult to grasp. Either information can travel backward in time, or the past remains mathematically undetermined within the theory until a measurement context is specified. These discoveries emerge from laboratories using the most sophisticated instruments ever built, operated by researchers trained in the most rigorous methods science has developed. They are not the result of sloppy measurement or wishful thinking. They represent the careful accumulation of evidence that reality at its most fundamental level operates according to principles that seem to contradict everything we know about how things should work. The disconnect between quantum mechanics and everyday experience is so profound that some physicists have begun to question whether quantum mechanics describes physical reality at all. Perhaps, they suggest, the theory describes something else entirely: the structure of information, the limits of knowledge, or the constraints on what can be predicted about future observations. In this view, quantum mechanics is not telling us what particles are doing when we are not looking. It is telling us what we can know about what they will do when we do look. This interpretation shifts the focus from objective reality to the process of measurement and observation. Rather than describing a world of objects with definite properties, quantum mechanics would describe the statistical patterns that emerge when observers interact with systems in various ways. The wave function would not represent the actual state of a physical system, but rather the information available to an observer about the outcomes of future measurements. Such a view preserves the predictive power of quantum mechanics, while avoiding the conceptual difficulties that arise from trying to interpret it as a description of objective reality. But it comes at a cost. It suggests that physics may have reached a fundamental limit beyond which we cannot penetrate the nature of reality itself. We may be limited, at least with current theoretical tools, to describing patterns in observation rather than underlying mechanisms. The possibility that science might encounter such limits is not new. Philosophers have long argued that there may be aspects of reality that lie forever beyond human understanding. What is new is the suggestion that we may have already reached such a limit in one of our most successful theories. Quantum mechanics works perfectly for making predictions and building technologies. Yet after nearly a century of development, it remains as mysterious as ever in its implications for the nature of reality. The situation becomes even more perplexing when we consider that quantum effects are not confined to microscopic particles in isolated laboratory conditions. Quantum mechanics governs the behavior of electrons in computer chips, the processes that power the sun, and the mechanisms that allow plants to capture light energy through photosynthesis. Recent research has revealed quantum effects in biological systems, including evidence that some birds navigate using quantum entanglement in their visual systems, and that quantum coherence may play a role in the efficiency of photosynthesis. The quantum world is not separate from the everyday world. It is the foundation upon which the everyday world is built. Yet the more we learn about this foundation, the more it seems to resist comprehension. We find ourselves in the position of inhabitants of a house who have discovered that the basement operates according to completely different architectural principles than the floors above, and that understanding those principles is essential to understanding why the house stands at all. This creates a curious situation for science as a whole. Physics prides itself on reductionism, the idea that complex phenomena can be understood by breaking them down into simpler components. Chemistry reduces to physics, biology reduces to chemistry, and so on down to the fundamental particles and forces. But if the fundamental level itself resists understanding in any conventional sense, what does this mean for the reductionist program? Can we truly understand the higher levels if the foundation remains mysterious? Some physicists have suggested that the answer may lie in abandoning reductionism altogether. Perhaps complex systems possess properties that cannot be understood merely by analysing their components. Perhaps the whole is not just greater than the sum of its parts, but operates according to entirely different principles. This would represent a fundamental shift in how science approaches the task of understanding nature. Others argue that the problem lies not with reality, but with our concepts and language. The mathematical formalism of quantum mechanics is precise and unambiguous. The conceptual difficulties arise only when we try to translate that formalism into everyday language and imagery. Perhaps the fault lies not with quantum mechanics, but with our insistence on understanding it in terms borrowed from classical physics and common sense. But this raises its own puzzles. If our most fundamental theory of nature cannot be understood in terms that make sense to human beings, what does this say about the relationship between human understanding and reality? Are we approaching the limits of what minds like ours can comprehend about the universe we inhabit? Or are we simply using the wrong conceptual tools and waiting for the right breakthrough to make everything clear? The questions multiply rather than resolve as our instruments become more precise and our experiments more sophisticated. Each new discovery in quantum mechanics seems to deepen the mystery rather than solve it. We learn more about what nature does while understanding less about why it does it, or what it means that it does it. Does it? The mathematics work flawlessly. Quantum field equations predict experimental outcomes to 15 decimal places. Particle accelerators confirm theoretical predictions with stunning precision. Computer chips function exactly as quantum mechanics demands they should. Yet something peculiar happens when physicists gather to discuss what these equations actually mean. The conversations become tentative, philosophical, almost apologetic. They have built a theory that works better than any scientific framework in history, and they cannot agree on what it describes. This disconnect runs deeper than academic disagreement. It touches something fundamental about the relationship between mathematical description and physical reality. Consider how a quantum physicist approaches a simple question. Where is an electron right now? The theory provides a wave function, a mathematical object that encodes probabilities for finding the electron in various locations. But ask what the wave function represents, and the answers diverge dramatically. Some say it describes the actual state of the electron, existing in multiple locations simultaneously until measured. Others argue it represents only our knowledge about the electron, with no physical reality of its own. Still others propose that the wave function splits reality into parallel branches, each containing a different version of the measurement outcome. These are not subtle variations on a theme. They are fundamentally different claims about the nature of existence itself. Yet all three interpretations make identical predictions about experimental results. This suggests something unsettling about the limits of empirical inquiry. We may have reached a point where our most successful theories describe the behaviour of nature without revealing its essence. The problem becomes more acute when we examine the role of measurement in quantum mechanics. The theory treats measuring devices as classical objects that produce definite results, while the systems being measured exist in quantum superposition until the moment of measurement. But this creates an arbitrary boundary. Every measuring device is made of atoms, which are quantum mechanical objects. The circuits that process signals, the displays that show results, the brains that interpret data, all are composed of particles that should, according to quantum mechanics, exist in superposition states. Where exactly does the quantum realm end and the classical realm begin? This question has no agreed-upon answer despite decades of investigation. Some propose that consciousness collapses quantum states, inserting the observer directly into the physical process. Others suggest that interaction with the environment gradually destroys quantum coherence through a process called decoherence. But decoherence does not solve the fundamental puzzle. It explains why quantum effects become harder to observe in large systems, but it does not explain why any system ever produces a single definite outcome rather than remaining in superposition forever. Recent experiments have made this boundary problem even more stark. In 2019, researchers demonstrated quantum interference effects in molecules containing over 2,000 atoms. These are not microscopic entities invisible to ordinary experience. They are substantial chemical structures that nonetheless behave according to quantum principles, existing in multiple locations simultaneously until observed. The boundary between quantum and classical appears to be far less clear than previously imagined. More puzzling still are experiments that seem to challenge our basic understanding of temporal sequence. In delayed choice quantum eraser experiments, researchers can decide how to measure a quantum system after the system has already passed through the measurement apparatus. Remarkably, within the experimental framework, this future decision appears to affect how the system's past behavior is described, not how macroscopic causality operates. The choice of measurement seems to reach backward in time to influence events that have already occurred. The implications are difficult to process. Either information travels backward in time, violating our understanding of causality, or the past remains undefined until future observations crystallize it into definite form. Neither possibility aligns with our everyday understanding of temporal sequence. Yet the experimental results are unambiguous and have been replicated many times with increasingly sophisticated setups. Consider what this means for the nature of physical events. In classical physics, an event either happens or does not happen, and once it has happened, it becomes an unchangeable fact about the past. But quantum mechanics suggests that some events may remain undetermined until future measurements decide their fate. The past, rather than being fixed and definite, appears to maintain a kind of malleability that persists until observation locks it into place. This temporal strangeness extends to other quantum phenomena as well. Quantum tunneling allows particles to traverse energy barriers. They lack the energy to surmount, appearing on the far side without having travelled through the intervening space. Recent measurements suggest that the time required for tunneling can be negative, with particles emerging from barriers before they have finished entering them. This does not enable faster-than-light communication or time travel, but it does reveal that even the simple concept of duration becomes problematic at quantum scales. The puzzle deepens when we consider that quantum effects are not confined to exotic laboratory conditions. Quantum tunneling is essential to nuclear fusion in stars, including our Sun. Without it, stars would never ignite, and the universe would remain cold and dark. Quantum entanglement appears to play a role in biological processes, from photosynthesis in plants to navigation in migrating birds. The quantum world is not separate from everyday reality. It is the foundation upon which everyday reality rests. Yet this foundation operates according to principles that seem to contradict everything we understand about how things should work. Particles exist in multiple states simultaneously until observed. Distant objects influence each other instantaneously without any apparent connection. Events in the past can be influenced by decisions made in the future. Properties of objects depend on the context in which they are measured. These are not speculative ideas or philosophical thought experiments. They are direct consequences of our most rigorously tested scientific theories. What makes this situation particularly striking is that quantum mechanics emerged from attempts to understand nature more precisely, not less. Early 20th century physicists were trying to resolve specific puzzles about atomic behavior and electromagnetic radiation. They were not seeking to overturn classical concepts of reality. The strangeness arose naturally from the mathematical formalism required to match experimental observations. Each new quantum principle was discovered reluctantly, often by physicists who hoped to find ways around its implications. Einstein spent decades searching for hidden variables that might restore classical determinism to quantum mechanics. He never found them. Bell's theorem later proved mathematically that no theory based on local hidden variables can reproduce the predictions of quantum mechanics. The strangeness appears to be unavoidable, built into the structure of nature at its most fundamental level. This creates a curious situation for physics as a whole. Science traditionally progresses by explaining complex phenomena in terms of simpler underlying principles. Chemistry reduces to atomic physics, biology reduces to chemistry, and so forth down to fundamental particles and forces. But what if the fundamental level itself resists explanation in any conventional sense? What does this mean for the entire reductionist program that has driven scientific progress for centuries? Some physicists have suggested that the problem lies not with reality, but with our concepts and language. The mathematical formalism of quantum mechanics is precise and unambiguous. The conceptual difficulties arise only when we try to translate that formalism into ordinary language and imagery. Perhaps we are demanding that nature conform to categories of thought that are simply inadequate for describing quantum phenomena. But this raises its own questions. If our most fundamental theory cannot be understood in terms that make sense to human minds, what does this reveal about the relationship between consciousness and physical reality? Are we approaching inherent limits of what intelligence like ours can comprehend about the universe it inhabits? Or are we simply using inappropriate conceptual frameworks, waiting for the right breakthrough to render everything clear? The questions multiply rather than resolve as experimental techniques become more refined. Each new quantum phenomenon deepens the conceptual puzzles rather than solving them. We discover more about what nature does while understanding less about why it does it or what it means. The closer we look, the more the familiar world dissolves into something unrecognizably strange. Modern quantum field Your theory describes particles as excitations in underlying fields that permeate all of space. But these fields exist in a quantum vacuum that seethes with virtual particles, constantly appearing and disappearing. Even empty space turns out to be full of activity, invisible to ordinary observation. The vacuum itself becomes an active participant in physical processes rather than a passive stage upon which events unfold. Recent discoveries have pushed these puzzles to even greater extremes. Researchers have identified quantum scars, persistent patterns that emerge in chaotic quantum systems and maintain their structure far longer than theory predicts. These represent a kind of quantum memory, where systems retain information about their past in ways that classical physics says should be impossible. The scars suggest that quantum mechanics contains organizing principles we do not yet understand, mechanisms that create order in circumstances where only randomness was expected. Other experiments have demonstrated quantum contextuality, revealing that quantum systems do not possess definite properties independent of how they are measured. The same system can yield different results depending on what other measurements are performed alongside the primary observation. This goes beyond the observer effect to suggest that quantum theory challenges whether properties can be defined independently of measurement context, in contrast to classical expectations. Properties appear to emerge from the act of measurement rather than existing prior to it. Perhaps most puzzling are recent claims about quantum computation and its relationship to the structure of reality itself. Some researchers argue that the extraordinary computational power demonstrated by quantum computers can only be explained if the calculations are somehow distributed across parallel universes. Each quantum bit would exist in superposition across multiple realities, allowing computations to be performed simultaneously in many universes, and the results combined into a single output in our universe. This interpretation remains highly controversial, with many physicists arguing that quantum computation can be understood without invoking parallel realities. But the debate itself reveals how quantum mechanics continues to challenge our basic concepts about computation, information, and the nature of physical processes. We can build devices that exploit quantum effects for practical purposes, while remaining uncertain about what those effects reveal about the structure of reality. The disconnect between operational success and conceptual understanding has become one of the defining features of modern physics. We possess theories that work with unprecedented precision for predicting and controlling natural phenomena. Yet those same theories resist interpretation in terms that align with ordinary human understanding. We find ourselves in the peculiar position of being able to manipulate nature at its most fundamental level, while remaining uncertain about what that level actually contains. This situation would be troubling enough if it were confined to quantum mechanics, but similar puzzles arise elsewhere in physics as well. General relativity reveals that space and time are not fixed background structures, but dynamic entities that bend and stretch in response to matter and energy. The theory makes extraordinarily precise predictions about gravitational effects, yet it offers no insight into why space-time should exist at all or what it is made of. Cosmology faces even deeper mysteries. Current observations suggest that ordinary matter and energy comprise only about 5% of the universe. The remaining 95% consists of dark matter and dark energy, substances that have never been directly detected and whose properties remain almost entirely unknown. We can measure their gravitational effects with great precision, but we have no understanding of their fundamental nature. Dark energy in particular presents a puzzle that borders on the absurd. Quantum field theory predicts that empty space should contain a vast amount of vacuum energy, but when physicists calculate the expected value, they get a number that is larger than the observed energy density of the universe by a factor of 10 to the power of 120. This represents the most spectacular failure of a theoretical prediction in the history of science. Yet the theory that produces this result works perfectly for describing particle interactions. The pattern repeats across different areas of physics. Our theories become more mathematically sophisticated and experimentally successful, while growing more conceptually mysterious. We understand how to calculate what will happen in various circumstances, but we understand less about why those things happen or what it means that they happen. The tools work better than ever, but their relationship to underlying reality becomes increasingly obscure. This creates a profound challenge for science as a way of understanding the world. The traditional scientific worldview assumes that careful observation and rigorous reasoning will eventually reveal the true nature of physical reality. But quantum mechanics suggests that nature may not possess the kind of definite, observer-independent properties that this worldview requires. The act of observation appears to play a fundamental role in determining what is observed, creating a circular relationship between knower and known that classical science was designed to avoid. Some physicists have embraced this circularity, arguing that science should abandon the goal of describing objective reality and focus instead on predicting the outcomes of observations. In this view, quantum mechanics does not tell us what particles are doing when nobody is looking. It tells us what patterns will emerge when we do look. The wave function does not represent the state of a physical system, but rather our information about the statistical regularities we can expect to observe. This pragmatic interpretation preserves the predictive power of quantum mechanics, while sidestepping its conceptual difficulties. But it comes at a philosophical cost. It suggests that physics may have encountered a fundamental limit beyond which the nature of reality cannot be penetrated. We may be confined forever to describing the patterns in our observations without ever understanding what lies behind those patterns. The possibility that science might reach such limits challenges some of our deepest assumptions about human knowledge and its relationship to the natural world. For centuries, the success of physics seemed to confirm that patient investigation would eventually reveal the true structure of reality. Each new discovery appeared to bring us closer to a complete understanding of how the universe works. But quantum mechanics suggests that this confidence may have been misplaced. We find ourselves in a curious position, knowing more about the behavior of nature than any previous generation, while confronting the possibility that the ultimate nature of reality may lie forever beyond our grasp. The universe appears to make less sense the closer we examine it, not because our methods are flawed, but because sense itself may be a category that applies only to certain scales of description and certain modes of investigation. Beyond those boundaries lies something that works perfectly well as mathematics, but resists translation into anything resembling ordinary understanding. We might expect that, as we develop better tools, more sensitive instruments, and more sophisticated mathematical frameworks, the fundamental questions about reality would gradually resolve themselves. Each new discovery should clarify what came before, filling in gaps and smoothing out inconsistencies until a complete picture emerges. But something peculiar happens when we trace this expectation through the actual history of physics. The more precisely we measure, the more anomalous the results become. The more sophisticated our theories grow, the more they seem to describe processes that have no clear analogue in ordinary experience. This inversion of expectation becomes particularly stark when we examine how measurement itself functions at the deepest levels of investigation. In everyday experience, measurement seems straightforward enough. We use tools to determine properties that objects already possess. The scale does not create the weight of an apple, merely reveals it. The thermometer does not generate temperature, simply displays what was already there. But this intuitive relationship between measurement and property begins to dissolve when applied to quantum systems. Consider what happens when physicists attempt to measure complementary properties of a single particle simultaneously. The precision with which position can be determined appears to be fundamentally linked to the imprecision that must be accepted in measuring momentum. This is not a limitation of current technology or technique. Heisenberg's uncertainty principle suggests that this trade-off is built into the fabric of reality itself. Improving the measurement of one property necessarily degrades knowledge of the other, not because of instrumental limitations, but because the properties themselves seem to exist in a kind of mutual exclusivity. The implications extend far beyond technical details about particle physics. If measurement at the fundamental level involves this kind of trade-off, then the very concept of complete knowledge about physical systems becomes problematic. Classical physics assumed that with perfect instruments and unlimited time, every property of every particle could be mapped with arbitrary precision. The universe seemed like a vast mechanism whose every component could eventually be catalogued and understood. But the uncertainty principle suggests that such complete knowledge is not merely practically difficult, but theoretically impossible. Recent experimental work has pushed these limitations to even more extreme territory. Researchers have demonstrated quantum effects in systems containing thousands of atoms, blurring the boundary between the microscopic realm where uncertainty principles apply and the macroscopic world of everyday experience. The quantum classical divide, which once seemed to provide a clear demarcation between strange quantum effects and familiar classical behaviour, appears to be far more fluid than previously imagined. What emerges is a picture where the tools of investigation themselves become entangled with what they investigate. The measuring apparatus cannot stand apart from the system being measured in the way that classical physics assumed. Instead, measurement becomes a kind of interaction that fundamentally alters both the measured system and the measuring device. The observer and the observed form a single, indivisible whole whose properties cannot be understood by analysing the components separately. This dissolution of the observer-observed distinction creates profound puzzles for scientific methodology. Science traditionally relies on the possibility of objective observation, the idea that properly trained observers using appropriate instruments can determine facts about the world that exist independently of the observation process. But quantum mechanics suggests that this independence may not exist at the fundamental level. The act of observation appears to play a constitutive role in determining what is observed. The puzzle deepens when we consider that quantum effects are not confined to exotic laboratory conditions or microscopic particles isolated from their environment. Quantum coherence has been discovered in biological systems, including evidence that photosynthesis in plants involves quantum superposition states and that some birds may navigate using quantum entanglement effects in their visual systems. The quantum world is not separate from the biological world. It is the foundation upon which biological processes are built. Yet this foundation operates according to principles that seem to contradict basic intuitions about how complex systems should behave. In classical systems, adding more components typically increases complexity in predictable ways. Understanding the parts provides insight into the behaviour of the whole, but quantum systems can exhibit properties that have no classical analogues and cannot be understood by analysing their components individually. The whole system can possess characteristics that are not present in any of its parts and cannot be predicted from knowledge of those parts. This breakdown of classical reductionism becomes particularly evident when examining quantum entanglement in multi-particle systems. When particles become entangled, their individual properties become undefined. The system as a whole possesses definite characteristics, but those characteristics cannot be attributed to any particular particle. Measuring one particle instantaneously affects all the others, regardless of the distances involved. The entire system behaves as a single, non-local entity that transcends ordinary spatial boundaries. Einstein found this non-locality so troubling that he dismissed it as an indication that quantum mechanics was incomplete. He believed that hidden variables would eventually be discovered that would restore local realism to physics. But decades of increasingly precise experiments have confirmed that entanglement is real and that no local hidden variable theory can reproduce the predictions of quantum mechanics. The universe appears to contain genuine, non-local connections that operate instantaneously across arbitrary distances. The confirmation of non-locality has implications that extend far beyond quantum mechanics. It suggests that the universe is not composed of separate objects interacting through local influences, as classical physics assumed. Instead, reality appears to be fundamentally interconnected in ways that transcend space and time. Events in one location can be correlated with events in distant locations without any apparent causal connection between them. This interconnectedness becomes even more puzzling when we consider the role of time in quantum processes. Recent experiments have demonstrated what researchers call quantum superposition of temporal order, where events can occur in multiple temporal sequences simultaneously until a measurement determines which sequence actually occurred. The familiar notion of a single, definite, temporal sequence of events gives way to something far more fluid and context-dependent. Other experiments have revealed quantum effects that seem to involve backward causation, where future measurements appear to influence past events. In delayed choice experiments, researchers can decide how to measure a quantum system after the system has already interacted with the measurement apparatus. Yet this future decision seems to retroactively determine how the system behaved in the past. The implications challenge basic assumptions about the nature of temporal sequence and causality. These temporal anomalies suggest that time itself may not possess the fixed, universal character that everyday experience suggests. Just as space has been revealed to be relative and context-dependent through relativity theory, time may be far more fluid and observer-dependent than classical physics assumed. The past may not be as definite and unchangeable as intuition suggests, remaining somehow malleable until future observations lock it into place. The accumulation of such findings creates a peculiar situation for physics as a whole. The mathematical formalism of quantum mechanics makes extraordinarily precise predictions about experimental outcomes. The theory has been tested more thoroughly than any framework in the history of science, and its predictions have been confirmed to remarkable precision across countless experiments. Yet despite this empirical success, there remains no consensus about what the theory actually describes. Different interpretations of quantum mechanics make radically different claims about the nature of reality. Some suggest that particles exist in multiple states simultaneously until measured. Others propose that measurement splits reality into parallel branches, each containing a different outcome. Still others argue that quantum mechanics describes only our knowledge about systems, not the systems themselves. These interpretations make identical predictions about experimental results, yet they paint completely different pictures of what exists. This situation is unprecedented in the history of science. We possess a theory that works perfectly for predicting and controlling quantum phenomena, yet physicists cannot agree on what the theory means. The mathematics provide an unambiguous algorithm for calculating probabilities, but the relationships between mathematical formalism and physical reality remains deeply mysterious. We have learned to use quantum mechanics with extraordinary effectiveness, while remaining uncertain about what we are using. The interpretive puzzles become even more acute when we examine the measurement problem in detail. Quantum mechanics treats measuring devices as classical objects that produce definite results, while the systems being measured exist in quantum superposition until the moment of measurement. But this division is arbitrary. Every measuring device is composed of atoms, which are quantum mechanical objects. The boundary between the quantum realm of superposition and the classical realm of definite outcomes has no clear location. Some interpretations attempt to resolve this problem by invoking consciousness as the agent that collapses quantum states. In this view, quantum superpositions persist until a conscious observer becomes aware of the measurement result. But this solution raises as many questions as it answers. What constitutes consciousness? Does a sophisticated computer count as conscious? What about a mouse or an insect? The boundaries of consciousness are no clearer than the boundaries between quantum and classical behavior. Other approaches suggest that environmental interactions gradually destroy quantum coherence through a process called decoherence. Complex systems become entangled with their surroundings in ways that wash out quantum interference effects and create the appearance of classical behavior. But decoherence does not solve the fundamental measurement problem. It explains why quantum effects become harder to observe in large systems, but it does not explain why measurements produce single definite outcomes rather than persistent superpositions. The measurement problem reveals a deep conceptual gap at the heart of our most successful physical theory. We can calculate the probability that a measurement will yield any particular result, but we cannot explain why any particular result occurs in any particular instance. The theory predicts statistical patterns with extraordinary accuracy, but it provides no account of individual events. This limitation appears to be fundamental rather than temporary, built into the structure of the theory itself. Recent developments in quantum information theory have added new dimensions to these puzzles. Quantum computers can perform certain calculations exponentially faster than classical computers by exploiting quantum superposition and entanglement effects. But the source of this computational advantage remains mysterious. Some researchers argue that quantum computers must be performing calculations simultaneously in parallel universes, combining the results through quantum interference. Others contend that quantum speedup can be understood without invoking parallel realities. The debate itself reveals how quantum mechanics continues to challenge basic concepts about computation, information, and the nature of physical processes. We can build devices that exploit quantum effects for practical purposes while remaining uncertain about what those effects reveal about the structure of reality. The technology works, but the underlying physics remains conceptually opaque. This opacity becomes particularly evident when quantum mechanics encounters other areas of physics. The theory describes particles as excitations in quantum fields that permeate all of space, but when physicists attempt to apply quantum mechanics to gravity and spacetime itself, the mathematical framework breaks down completely. The equations produce infinite results that have no physical meaning. Despite decades of effort, no one has successfully constructed a quantum theory of gravity. This failure suggests that our current understanding of quantum mechanics may be incomplete in fundamental ways. The theory works perfectly for describing particle interactions, but it cannot be extended to encompass the gravitational field that curves spacetime itself. Either quantum mechanics requires major modifications, or gravity operates according to principles that lie outside the quantum framework entirely. Both possibilities would represent revolutionary changes in our understanding of physical reality. The conceptual difficulties multiply when we consider cosmological questions about the universe as a whole. If quantum mechanics applies universally, then the entire cosmos should exist in a quantum superposition of all possible states until measured. But measured by whom? There is no external observer outside the universe who could collapse its wave function. Some interpretations suggest that the universe branches into parallel realities corresponding to all possible measurement outcomes. Others propose that the universe somehow measures itself through internal observers like us. These cosmological puzzles reveal how quantum mechanics pushes against the boundaries of coherent thought. The theory that describes microscopic phenomena with unparalleled precision becomes increasingly difficult to interpret when applied to the larger scales of space and time. We find ourselves with a framework that works perfectly within certain domains, while becoming conceptually unstable when extended beyond those boundaries. The situation creates a profound challenge for scientific understanding. Physics traditionally progresses by developing theories with ever broader scope and deeper explanatory power. Each advance should illuminate previously mysterious phenomena and unify apparently disparate domains under common principles. But quantum mechanics seems to resist this pattern. The more successfully we apply the theory, the more mysterious it becomes. The more precisely we test its predictions, the stranger its implications appear. We find ourselves in the curious position of possessing the most empirically successful theory in the history of science, while remaining deeply uncertain about what that theory reveals about the nature of reality. The mathematics work flawlessly, the experiments confirm the predictions, the technology functions as expected, yet the relationship between formalism and physical reality remains as puzzling as ever. We have learned to manipulate quantum systems with extraordinary precision while remaining uncertain about what quantum systems actually are. This disconnect between operational mastery and conceptual understanding may represent something unprecedented in the history of human knowledge. Previous scientific advances typically brought practical control and theoretical comprehension together. Understanding planetary orbits led to both better navigation and clearer concepts about gravitational force. Grasping electromagnetic theory enabled both new technologies and deeper insight into the nature of fields and radiation. But quantum mechanics seems to decouple these traditionally linked aspects of scientific progress. Perhaps this decoupling reveals something important about the limits of human understanding itself. Our concepts and language evolved to navigate a world of medium-sized objects moving at moderate speeds. The categories of thought that serve us well in everyday life may simply be inadequate for comprehending phenomena that operate according to quantum principles. We may be asking quantum mechanics to conform to conceptual frameworks that are fundamentally inappropriate for describing quantum phenomena. But if our most fundamental theory cannot be understood in terms that make intuitive sense to human minds, what does this suggest about the relationship between consciousness and physical reality? Are we approaching inherent limits of what intelligence like ours can comprehend about the universe it inhabits? Or are we simply waiting for the right conceptual breakthrough to render everything clear and comprehensible? The questions multiply rather than resolve as our experimental capabilities become more sophisticated and our mathematical tools more powerful. Each new quantum phenomenon seems to deepen the conceptual puzzles rather than solving them. We discover more about what nature does at the fundamental level, while understanding less about why it does it, or what it means that it does it. The closer we look at the foundations of reality, the more those foundations seem to recede beyond the reach of ordinary comprehension, leaving us with tools that work perfectly and concepts that make no sense at all. The strangest thing about working in a physics laboratory is how normal it feels. You adjust dials, read displays, record numbers in notebooks. The instruments hum quietly. Coffee grows cold on cluttered desks. Everything appears orderly and familiar, the way precision work should look. Yet the numbers you're recording describe a reality that seems to operate according to principles that make no intuitive sense whatsoever. The more carefully you measure, the more the measurements seem to point towards something that cannot quite be grasped by ordinary thought. This disconnect becomes particularly acute when you realize that the same equations producing these baffling results also enable the construction of devices that work with extraordinary reliability. The computer processing these words operates according to quantum mechanical principles that no physicist claims to fully understand. The laser reading data from optical storage relies on quantum properties of light that seem to contradict basic assumptions about the nature of physical objects. We have learned to build technologies based on phenomena that resist comprehension, creating a peculiar situation where our most practical successes emerge from our deepest conceptual failures. Consider how measurement itself has evolved as instruments have become more precise. Early physicists assumed that better tools would eventually reveal the true properties of objects with arbitrary accuracy. The goal was to minimize the disturbance caused by measurement until it became negligible, allowing the intrinsic characteristics of systems to be determined without interference. This program worked remarkably well for centuries, yielding increasingly detailed knowledge about planetary motions, electromagnetic fields, and atomic structure. But something unexpected happened when measurement precision reached certain thresholds. Rather than revealing clearer pictures of underlying reality, more accurate measurements began to expose fundamental limitations that appeared to be built into nature itself. The precision required to probe these limitations creates its own peculiar challenges. Modern experiments often involve isolating single particles in elaborate apparatus designed to shield them from environmental disturbances. Temperatures must be maintained within microkelvin of absolute zero. Vibrations must be dampened to levels that would make the apparatus sensitive to gravitational waves from distant galaxies. Magnetic fields must be controlled to precisions that require accounting for the magnetic signatures of nearby subway trains. The effort required to create conditions pure enough for certain measurements has become so extreme that the experimental setups themselves represent some of the most isolated environments ever created by human technology. Yet even under these extraordinary conditions, the measurements reveal behavior that seems to violate basic principles about how information can be transmitted, how objects can exist in space, and how events unfold in time. Particles separated by meters or kilometers continue to influence each other instantaneously when one is measured. Individual objects appear to pass through multiple paths simultaneously until observation forces them to choose a single trajectory. Properties that seem definite and objective turn out to depend on which other properties are measured alongside them. The more carefully controlled the experimental conditions become, the more clearly these anomalous effects emerge. What makes this situation particularly puzzling is that the mathematical description of these phenomena works perfectly for predicting experimental outcomes. Quantum field theory can calculate interaction probabilities to 15 decimal places of accuracy. The equations governing electromagnetic and weak nuclear forces have been confirmed across energy scales spanning more than 20 orders of magnitude. The mathematical machinery operates with a precision that surpasses any previous scientific theory. Yet the physical interpretation of what the mathematics describes remains as mysterious as ever. This precision becomes even more remarkable when you consider that the same theoretical framework must account for phenomena occurring across vastly different scales of space and time. The equations that describe electron behavior in atomic orbitals also govern the interactions that power stellar fusion. The quantum principles that operate in laboratory experiments also appear to play essential roles in biological processes like photosynthesis and possibly even consciousness itself. The mathematical structure seems to capture something universal about the way nature operates, yet that universality extends to domains where human intuition provides no reliable guidance. The universality creates its own interpretive challenges. If quantum effects appear at every scale from elementary particles to biological systems, then the boundary between quantum and classical behavior becomes increasingly difficult to locate. Recent experiments have demonstrated quantum coherence in molecular systems containing thousands of atoms, far larger than anything that was thought to exhibit quantum properties just a few decades ago. The dividing line between the microscopic realm, where quantum effects are expected, and the macroscopic world of everyday experience appears to be far more fluid than previously imagined. This fluidity becomes particularly evident when examining how quantum systems interact with measuring devices. The theory requires that measuring apparatus behave classically, producing definite numerical results rather than existing in quantum superposition. But every measuring device is composed of atoms and electrons that should, according to the same theory, exhibit quantum behavior. The boundary between the quantum system being measured and the classical device performing the measurement has no clear physical basis. It exists only as a conceptual division that allows the mathematical formalism to function, not as a feature of the physical world itself. Some physicists have suggested that this boundary emerges naturally through environmental interactions that destroy quantum coherence in large systems. Complex objects become entangled with their surroundings in ways that wash out quantum interference effects and create the appearance of classical behavior. But this decoherence process does not solve the fundamental puzzle of why measurements yield single definite outcomes rather than persistent superpositions. The mathematics can describe how quantum effects become harder to observe in large systems, but they cannot explain why observation produces the specific results that it does in individual cases. The inability to predict individual measurement outcomes represents a fundamental departure from classical scientific methodology. Previous theories aim to provide deterministic accounts of natural phenomena, explaining not just statistical patterns, but the specific behavior of individual systems. Newtonian mechanics could predict exactly where a planet would be at any future time. Maxwell's equations could calculate precisely how electromagnetic fields would propagate through space. But quantum mechanics provides only statistical predictions, giving probabilities for various possible outcomes without explaining why any particular outcome occurs in any particular instance. This statistical character becomes even more puzzling when applied to measurement situations involving single particles. When an individual electron encounters a detector, the theory can calculate the probability that the detector will register a signal, but it cannot explain why the detector either clicks or remains silent in that specific instance. The mathematical formalism treats each measurement as a fundamentally random event, yet the randomness appears to emerge from completely deterministic equations. The theory predicts the statistical distribution of many measurements with extraordinary accuracy while providing no account whatsoever of individual results. The randomness itself has characteristics that seem to transcend ordinary statistical fluctuations. In classical systems, Apparent randomness typically reflects incomplete knowledge about the initial conditions or hidden variables that influence the outcome. Given sufficient information about a coin flip, you could in principle predict whether it lands heads or tails. But quantum randomness appears to be genuinely fundamental, not reducible to ignorance about hidden factors. Bell's theorem and subsequent experimental tests have demonstrated that no theory based on local hidden variables can reproduce the statistical predictions of quantum mechanics. The randomness seems to be an irreducible feature of nature, rather than a reflection of limited knowledge. This fundamental randomness creates profound puzzles about the nature of causation itself. If measurement outcomes are genuinely random, then the connection between causes and effects becomes problematic in ways that classical physics never anticipated. The same initial conditions can lead to different outcomes without any apparent reason for the difference. Events occur without causes that can be specified within classical deterministic frameworks, at least in any sense that would be recognizable from a classical perspective. The universe appears to contain genuine novelty that emerges from quantum processes in ways that cannot be predicted or explained by prior conditions. Recent experimental work has pushed these puzzles into even stranger territory. Researchers have demonstrated quantum effects that seem to involve backward causation, where future measurements appear to influence past events. In delayed choice experiments, the decision about how to measure a quantum system can be made after the system has already interacted with the measurement apparatus. Yet this future decision seems to retroactively determine how the system behaved in the past. The temporal sequence of cause and effect, which seems so fundamental to ordinary experience, becomes fluid and context-dependent at the quantum level. These temporal anomalies suggest that time itself may not possess the fixed, universal character that classical physics assumed. Just as space has been revealed to be relative and observer-dependent through relativity theory, time may be far more malleable and contextual than everyday experience suggests. The past may not be as definite and unchangeable as intuition demands, remaining somehow open to influence until future observations crystallize it into definite form. The familiar notion of a single, objective, temporal sequence of events gives way to something far more complex and interdependent. The malleability of temporal sequence becomes even more striking when combined with the non-local character of quantum entanglement. Measurements performed on entangled particles can instantaneously influence each other regardless of the spatial separation between them, apparently transcending the speed of light limitation that governs all other physical interactions. But if the temporal sequence of measurements can also be indefinite until future observations determine it, then the familiar concepts of space and time begin to lose their organizing power for understanding quantum phenomena. This dissolution of spatiotemporal structure forces a reconsideration of what it means for events to be causally connected. Classical causation requires that causes precede effects in time, and that influences propagate through space at finite velocities, but quantum correlations seem to operate outside these constraints, creating connections between events that are neither spatially nor temporally local in any conventional sense. The universe appears to contain genuine, non-local connections that transcend ordinary space-time boundaries, yet these connections cannot be used to transmit information or energy in ways that would violate relativity. The restriction on information transmission creates its own puzzles about the relationship between quantum correlations and classical communication, entangled particles can influence each other instantaneously across arbitrary distances, yet this influence cannot be harnessed to send messages faster than light. The correlations are real and measurable, but they cannot be exploited for practical communication purposes. This combination of genuine non-locality with preserved relativistic causality represents a delicate balance whose physical basis remains deeply mysterious. Perhaps the most unsettling realization is not that the universe defies our expectations, but that our expectations themselves may be the problem. We approach the deepest questions about reality armed with concepts forged in a world of medium-sized objects moving at comfortable speeds, and we express surprise when those concepts prove inadequate for describing phenomena that operate according to entirely different principles. The failure may not lie with quantum mechanics or relativity or any of the mathematical frameworks we have constructed. The failure may lie with our insistence on translating mathematical precision into the familiar language of everyday experience. Yet this creates a peculiar situation for conscious beings trying to understand the reality they inhabit. If our most successful theories resist comprehension in terms that make intuitive sense, what does this suggest about the relationship between mind and nature? Are we approaching fundamental limits of what intelligence like ours can grasp about the universe? Or are we simply waiting for the right conceptual breakthrough to render everything clear? The question itself may be unanswerable, not because the answer is hidden, but because the categories in which we pose the question may be inappropriate for the phenomena we are trying to understand. What remains is the peculiar beauty of this predicament. We find ourselves in possession of mathematical tools that work with unprecedented precision while describing processes that seem to transcend ordinary comprehension. We can manipulate nature at its most fundamental level while remaining uncertain about what that level contains. We have learned to conduct the symphony of quantum mechanics perfectly while remaining unsure whether the orchestra exists when no one is listening. The universe appears to challenge our intuitive sense-making the closer we examine its foundations, not as a failure of science, but as a revelation of how much deeper the mystery runs than we had ever imagined. In this deepening mystery, perhaps, lies something more valuable than answers: the recognition that reality is far stranger and more wonderful than our concepts can contain.